All right. Hey everyone, welcome to Atomic Design. My name is Sebastian. I'm the global guide manager here at Atomic. We talked about Atomic. We were founded in 2010. We're a consulting agency that focuses on mobile apps and web apps. It's kind of our story in a nutshell. So we're really pleased to be hosting DataPhilly tonight. Michael, welcome to Atomic again. Make yourselves at home, enjoy the talks. If there's anything I can do for you, let me know. If you need help with me, let me know. And again, enjoy yourselves, make yourselves at home, have a good night. Off to you.
Thank you. Thanks again to Atomic. This is a really awesome space, and thanks for having us and providing refreshments and pizza. Just a quick announcement for the first talk here. We do have time for lightning talks. I know a few people contacted me, so if you happen to want to get a lightning talk, just after the first talk, I'll ask you if you want to come up, and we'll have time for that. Brandon, did you want to introduce our speaker?
Yeah, sure. All right. So hi everyone, thanks for coming out tonight. Hope the pizza and beer has been good so far. It's certainly been good to me. I'm feeling pretty good. So I'm excited to introduce Sebastian Raschka, maybe one day, probably never Dr. Sebastian Raschka. He's so infamous for not graduating before asking questions on Quora on why he's not graduating.
But you should mention it's my 5th year. I'm not in.
Yeah, he's still technically on track, but anyway. So Sebastian and I went to grad school together at Michigan State. And he's been studying, biochemistry?
Computational biology.
I'll just say computational biology. Every single time I try to say this, I get it wrong. But I think what he's perhaps more well known for is, one, writing the Python machine learning book that was published, a year and a half ago?
September 2015, yeah.
Yeah, so,
1 year.
which has been one of the best-selling machine learning books since it was published, which is pretty cool. I was happy to have a part in that book. I wrote the foreword for it. Although we should tell PAC that I'm still waiting for my royalty checks. Maybe they'll come someday, I hope. I should have signed a contract. Take that as a lesson, sign a contract. I think he's also very well known as just being a very prolific contributor to the Python open source community, both in terms of code, writing several very cool packages, including it's a watermark package that I use pretty regularly. It's very useful. Also just writing some very useful tutorials on his blog and all over the place about machine learning, Python, data analysis, data visualization, all that good stuff. And so he was out here visiting me, and I was secretly trying to recruit him to come work with us. But I figured, hey, why didn't he come give a talk at DataPhilly too? So I came to talk about machine learning and performance evaluation, and I believe model selection as well. So with that, I will stop rambling and taking up all of his time so he can start talking about this cool topic.
Hi everyone, and thank you, Randy, for the nice talk, or maybe short introduction. I'm not sure, it wasn't quite short, but I appreciate it. Thanks for the nice work. And I'm happy to be here. Honestly, I planned on a little vacation at Randy's place, but it turned out it will be a little bit more exciting, right? I mean, we all like to talk about data stuff, so I'm happy to be here, and thanks for the invitation. And I think I should maybe get started because, I have a huge topic, and I try to just narrow it down to the maybe more interesting or essential parts that are maybe hopefully useful as a teaser to think about in different projects that you are working on. Because I think model evaluation and performance metrics and all these kind of things are very important if you develop algorithms or if you just compare algorithms or apply them to your research problems. It's not only as a researcher but also as a practitioner. And so maybe then why do we even bother about performance evaluation? I mean, not on a trivial level like, hey, we want to have a good model, but I would say we can break it down into 3 different maybe subtasks that are somewhat related to each other. And I think my kind of take on that, what I think is are the 3 essential things why we care about evaluating machine learning models, predictive models, like classifiers or regression models, would be, for example, we are of course interested in the generalization performance. How well does our model perform on new data, unseen data, future data? We train it on a training set, but ultimately we are trying to make predictions on new data about the future maybe. And this is of course the big umbrella term, but also when we build our models, we not just we just don't use an algorithm and run it over the training data and are done with it. What we usually do is we use different hyperparameter settings, like we tune the knobs of our learning algorithm, and we come up with a selection, with a let's say 20 models, 10 models with all different settings. They produce different hypotheses, and we want to select the one that performs best. So how do we know which one performs best? Of course, we can take the one that has the highest, let's say, average accuracy or something like that. But we will talk about it a little bit more in detail later, why this can sometimes be a little bit misleading. And then, of course, algorithm selection. So it's not only that we are tuning the internal knobs of our particular algorithm, because sometimes we just don't know which algorithm will perform best on a particular data set. We want to explore different algorithms. And there's also a little bit of danger of becoming a little bit biased or overfit our training data, and then our estimate is not what it should be. It's a little bit optimistically or pessimistically biased. And that is basically, I think, the topic of today. We'll talk a little bit about common pitfalls and good practices in model selection and algorithm selection. And I'm not sure, I hope you are all familiar with predictive models, classifiers, and let's say regressors. So, and usually when you look at literature, people use the two terms like variance and bias when they talk about performance estimates or different models. And for those who haven't heard about it, like just to that we are on the same page, to talk a little bit what is bias and variance, what do we mean by that? So I draw this fancy projectile launcher this morning. It wasn't that easy in PowerPoint, honestly. So what I want to say here is, so let's say our target here, it's not a cross, it's let's say our performance estimate, the true performance of a model, and how the projectile launcher comes in. So it's our tool that makes our prediction, how well we can maybe predict the true performance of our model. And then let's have our launcher launch some projectiles, and let's say they land, the projectiles land somewhere where the dotted lines end. And the spread of our different guesses, that's the variance, so our spread our estimates. And for example, we have different values that we maybe estimate, and this is the variance of our estimate. It's not always landing on the same point, we have a certain spread. And if we take the average of that and compare it to our target variable, the difference between the average estimated value and our target value, that would be our bias. So in this case, if we think about the x-axis as 0 to 100% accuracy, that would be a pessimistic bias, because all our guesses are underestimating the true performance here. And maybe a diagram that you've seen in some textbook that maybe fits better on one slide, it would be the classic dartboard, where here the different squares should simulate different guesses by us when we want to estimate the performance of a model. And this neatly summarizes the different kind of pitfalls of a low variance, high variance of our estimate and a high bias. So in the upper left corner, that is basically the ideal. We want to have an estimate that has a low bias and a low variance. So think of the center here as a point estimate, and we want to, with our red squares, we want to hit into the target, into the center. And if we have a low variance and low bias, we kind of hit the center almost all the time pretty accurately. If our variance is high, in the right upper corner, our estimates are kind of spread around the middle. And if we have a bias in one direction, for example, and a low variance, all our estimates end up somewhere systematically a little bit off. And in the worst case scenario, we have a high variance and a high bias, so our estimates are not only off by a certain value, but they also spread around this off value. And maybe for people who are more familiar with the statistical notation, here on the right, the bias is basically just the expected estimated value, or let's say the mean of our estimates minus a true parameter that we want to estimate. and the variance is just a statistical variance. So that's just so that we are familiar with the terms bias and variance. When it will come up a lot in machine learning literature when you look at model performance evaluation and different models. And also one thing I think is very important to think about is when we are talking about model performance estimates. Sometimes it's not really always important to have a low bias, because when we compare different algorithms, for example, when we do the model selection, we rank different models. So we have to think about a little bit about absolute and relative performances. And by that I mean, are we, if every estimate is shifted by a certain value, has the same bias, then it doesn't matter if we rank our models. So when I go back to our three initial tasks that we defined when we are interested in model evaluation, like the generalization performance, model selection, and algorithm selection. So the first part would be we build a model and for someone or a collaborator, and our collaborator want to know how well does it perform on a new data set, and he wants a pretty accurate value. Then we really care about the absolute performance. But if we have, let's say, 5 models, and we just want to select the best performing one, it doesn't matter if we underestimate the performance by 10% for each model, because we still get the same ranking. We would rank them in the same order anyway. So in these two tasks, we don't worry so much about bias, but the variance is more important, because if our estimate is really spread, we can't really trust it. Is it really better, or is it just a particular training and test split that makes it look better in this case? What happens if I change my random seed? Does it still perform well or not? And this is something that we will get also briefly into today. And before I talk a little bit more about that, so the simplest way maybe to evaluate a model is to take our data set and split it into a training and a test set. And we use the training set for model fitting and the test set for model evaluation. And of course, it's really important that we don't use the test set twice in any procedure, because then our test data kind of leaks. We use information that we shouldn't have known, because what we do is when we have a test set, we pretend that it is new real-world data that we haven't seen before, because what we want is we want to see how a model will perform on new data. And if we compare different models on the performance on the test set, we kind of cheat. We say, okay, which model performs best on the test set, and we know this test set, so it's kind of indirectly optimizing model performance on the test set. And also, when we do such a split, it's a very simple scenario. We split a data set into a train and test set. There are also some pitfalls to think about. So when we have different data sets of different sizes, we also have to think about what proportion should we withhold as a test set. And usually people use something like 70% training data, 30% test data, something around that, or 80-20 or 90-10. But it really matters how big our data is. In an ideal world, we would have unlimited data. We would have a really unlimited big, let's say 10,000, 100,000, 1 billion training samples. And each time we want to evaluate a model, we can generate a new test set from an underlying distribution. But unfortunately, in the real world, we don't know this generating distribution, so we have to make use of our data as best as we can. And so thinking about how bias and variance can influence such a training test split. So for example, if I have let's say this is a 70-30 split, and to think a little bit about what happens in terms of the bias of our model estimate, what happens if I make our test set larger? So if I increase the number of test samples, that means that I decrease the number of training samples. And usually, the fewer training samples I have, the worse the model performs if it's, for example, overfitting or hasn't reached its capacity yet. So that essentially means the less training set data we have, the higher our pessimistic bias. So our model has fewer data points to learn from. So removing valuable data points from the training set in favor of the test set kind of increases our pessimistic bias of our estimates. And maybe one intuitive explanation for this is, you probably have all seen like learning curves. So a learning curve is basically a curve where we have a model that is trained on different subsets of a training set. So here in this case, I took the MNIST data set. It's a data set of 50,000 training samples. All are digits, 0 to 9. And these are just handwritten digits, and it's a useful benchmark data set that we use to see if a model can classify which digit this is in the image. It has 50,000 images, and for just demonstration purposes, I just took 5,000 of these images, so 10% of the training data in MNIST. And I withhold 1,500 samples as test set, and then I have different splits of the training set. So on the left, I start with, I don't know, but I think it was 100 training samples, then I go up to 500 and something like that. So I have different sizes of the training set, so each square is a different size on the axis of the training set. As we can see here, as my training set grows, the overfitting becomes smaller. The overfitting can be kind of indicated between the gap between test and training performance. And the more data this model gets, the better the test performance. So usually we don't want to retest our model on the test set, but this is just for demonstration purposes to see how the test set behaves with, or how the model behaves if it gets more data to learn. And so at some point it may reach a capacity where it doesn't improve anymore, but until we reach this capacity, usually more training data should make a positive impact on the model, so decreasing the pessimistic bias. So if I would just say I use 10,000 training samples, then our model would be more pessimistically biased as if I would use, let's say, 50,000 images, just based on the trend that we can kind of guess here. And vice versa, so if I increase the number of training samples, so we said by increasing the training set, we can maybe improve also our model estimate, make our model better, and have a less pessimistically biased estimate. So it would decrease the pessimistic bias. But on the other hand, if we make our training set larger, what happens is, unfortunately, our variance of our estimate increases. So we have a larger variance. And why is that? So the problem is, if we have a smaller test set, a larger proportioned training set, the problem becomes that it's really more sensitive, our model is more sensitive to how we split this data. So if we change, for example, hyperparameter, if we change the random seed to make the split, we have maybe different results because it really depends which particular samples end up in the test set. And maybe a more intuitive explanation would be each time we do a subsampling or resampling, we kind of change the properties of a distribution. So we think or we assume that the training set and the test set, that they have the same underlying distribution. So what we do is we say, okay, our training set or our data set is representative of the real world. We want to train a classifier that does well in the real world, and our training set is a representative sample. And if we split it into two parts, a training and a test set, we also say our training set is a representative sample of our real world, and our test set is a representative sample of our real world. But each time we do such a split, we kind of change the distribution a little bit because due to random sampling. And here in this case, for example, in the middle, at the top, when I start out, let's say I know the generating distribution. It would be a 2D Gaussian distribution. And when I draw 100 samples from the Gaussian distribution here, and I draw 1,000 samples here, we can already see the distribution looks a little bit different than the true distribution. It's an approximation. It's just approximating this distribution. And then if I split it further, here on the left, you can see it even looks more different than the original one. And here, the different rows are 3 different splits. I just use different random seeds and split it into 7% training data and test data. And you can see each of them looks a little bit different. And on the right side, it's the very same thing, but I use 1,000 samples instead of 100. So each time we do a split, we can see that somehow we change the distribution. And on the right side, if we have more samples, it's not as bad as we have fewer samples. So, and also the idea is basically if we increase the size of the training set by decreasing the size of the test set, we introduce a certain variance because suddenly all our distributions are a little bit different. One trick I would always recommend it if you do a classification, for example, is to stratify your split so that you maintain class proportions. So, for example, in scikit-learn, it's just one example, they have a stratified parameter in the train test split. It was just added in, I think, scikit-learn 0.17, so not everyone knows that it's not a default parameter. But I, for example, recommend you to look at it, especially if you work with a small data set, so that your training and test set have the same proportion of class labels. So, and just to see, to bring home this point of variance in practice, so let's say I do a training and test split, and I evaluate my model and do this, let's say, 50 times here. Okay, so I do this 50, no, that was not too far. 50 times, and each time I plot the accuracy I get. So I split my data set. Here I use the iris data set. The iris data set has 150 flowers, so a very small data set, 3 different classes, and I use the simple 3 nearest neighbor classifier. And the first time, so the first bar would be my first split, I get 100% accuracy. So on the 50% test data set, my classifier is 100% accurate, so I would think this is really a great classifier, doesn't make any mistake. But if I change the random seed, split my data set again, train the very same, or have the very same classifier, it's a lazy classifier, so it just looks up training sets when I classify a new test set sample. It gets maybe, 95% accuracy. So something changed, although everything is the same, but I changed the random seed. And if I repeat this 50 times, you can see there's a kind of a variance between my estimates. So it's sometimes maybe you can't 100% trust just one point estimate because there's a certain variance of your estimate. And the average, for example, may be more robust to take the average, which would be 95% here. And so this is for a 50-50% split. And as I said before, if we increase the training set size, increase the test set size, it becomes more kind of sensitive to how we split it. How the random seed should even make a larger difference. So I repeated the same thing here on the right using a 90-10 split. So the average accuracy increased a little bit. So remember, the smaller the training set we said before, the higher the pessimistic bias. You can kind of guess this. I mean, 95, 96 is not a huge difference, but it's kind of maybe underlining this point that the smaller training set maybe is a little bit more pessimistically biased. And here on the right, you can see the variance increases a lot if I kind of increase the train test split. So in practice, it's maybe not a good idea to do such a train test split to evaluate models. I think if you do like deep learning, you usually work with large data sets where you have million samples. So I think in these cases, it's maybe not so much of a difference because, like I said before, with the distribution, if you have a large data set and you subsample, so the subsampling shouldn't make that much of a difference. But the smaller your data set is, the more precious your data becomes. And you probably, most of you have heard of it. One better way, I think, maybe to evaluate a model would be k-fold cross-validation. And k-fold cross-validation, what you do here is you define k, let's say in this example, k equals 5. So we have 5 iterations, and in each iteration we take a data set and split it into 5 parts. And the blue part, let's say this is our test or validation fold, and in each part we have a distinctive validation fold. And then we also train the model 5 times. Each row will be 1 iteration. And we get a performance and accuracy for each of the 5. And then we compute the average of these 5 performances, and that is our, let's say, cross-validation performance. So here, it would be a little bit more robust because we have different splits. So like I said before, depending on how we split, we may get a 100% accuracy, maybe a 95% accuracy, depending also on the data set. So this would be more like an average, more robust way. And also here, what's interesting is that the test folds are independent of each other, so we don't repeatedly test the test point. For example, in the one before that I showed you here, the repeated train test split test set can maybe never be part of any test training sample, and the particular sample can never be a test sample. It depends on how often we repeat it, and it's kind of stochastic. And so how to use this k-fold cross-validation in typical model evaluation pipeline. So again, so we use, for example, the training fold here to use a certain set of hyperparameters. If we have a model, we set we want this hyperparameters, maybe the default hyperparameters. Then we run our learning algorithm and get a model. And then for the test fold, we take the same model and feed it the validation fold and get the prediction. And so we can use k-fold cross-validation for model evaluation if we have a fixed hyperparameter set. So, but what if we want to tune our hyperparameters? And for those who are not familiar with hyperparameters, it's a very simple term. It's hyper sounds a little bit fancier than it really is. So it's basically the tuning knob of your learning algorithm. So in this case, it would be a simple logistic regression. In a logistic regression, you want to fit certain weight parameters to minimize the cost function. And these would be the model parameters, the weight that we want to learn. But if we, for example, use something like gradient descent, an optimization algorithm, we have to specify how often do we want to iterate over the training set. It's basically a parameter of the algorithm itself. So we say it's a hyperparameter. And same with, let's say, the regularization strength. We add a certain penalty to our cost function to, let's say, prevent overfitting. It would be like an additional parameter of our learning algorithm. It wouldn't be a model parameter, for example. So how do we kind of like sample different hyperparameter values, and how do we evaluate different models that were produced by using different values? So here we can also use k-fold cross-validation, but I think also a good way to think about is we saw estimates can have a certain variance, and a common, let's say not trademark method that is used in practice is called the law of parsimony. It's called the one-side error method. It kind of relies on the idea of the law of parsimony or Occam's razor. So if we have two equally well-performing models, for example, we say we should maybe choose the simpler one by doing something more complex if the simpler solution already works. So simpler solutions are maybe less likely to overfit or things like that, or just easier to learn. So we want to prefer the simpler method if two methods perform equally well. And in the one-sided error method, for example, we, let's say, tune different hyperparameter values. We get different models. And then what we do is we, for example, can plot the model, compute the standard error of our cross-validation estimate. And here in this example, I use a kernel SVM. It has a gamma parameter, and the gamma parameter basically defines the influence of each single data point. So the larger the gamma parameter, the larger the influence of each training point. I will show you how it looks like in practice later, or in the next slide actually. And here, the error bars are the standard errors of our cross-validation estimate. And there are like, I would say, 1, 2, 3 that perform almost equally well, but the one here at gamma 100, gamma 10, would be maybe the best performing one, and we can say this one lies within one standard error of this one. So maybe we should take a look at these models and take the simpler one. And here's how they look like in 2D. Like I used a two-dimensional data set, the iris data set again. Oh, sorry, it's a concentric circle data set. And our goal here was to classify red squares versus blue triangles. And the SVM, depending on how we choose our gamma value, produces a different decision boundary. So if we choose a very low gamma value, we get almost a linear decision boundary, or kernel SVM. And if we increase the gamma value, now we get like a quadratic or a square circle here. And if we increase our gamma parameter further, our model will be a very complex decision boundary. And I highlighted the 3 points up in the left, the accuracy estimates of cross-validation. And for example, as we can see, the highest one is a very complex decision boundary, but it doesn't perform necessarily much better in terms of accuracy than the not very simple, but simpler one. And in the upper right, this may be too simple. So it's not powerful really enough to distinguish between anything here. It's almost random. So here, according to the one standard error method, I would say we should maybe prefer the simpler one if possible, by doing something as complex as right there if it's not really, obviously not really better than the other one. And maybe, so to really integrate cross-validation for model selection in a pipeline that we would do in a normal project. So maybe let's walk through it step by step. So first, we start with our data set. We have our data set, we have class labels, or in, let's say, regression analysis, we have our target values. and then we split it into a training data set and a test data set. So that's the usual step. Sometimes if we have a very small data set, we can also maybe not withhold data, but then we have to choose a different approach. So or if we, for example, are not that much interested in the absolute performance, but only want to rank different models, then maybe we can skip the test data set. But usually that is our typical setup for model evaluation. And then in the second step, we choose our learning algorithm, and we choose different hyperparameter values. There are different methods like grid search or randomized hyperparameter search or Bayesian optimization. So what's important is we have different hyperparameter values, and using our learning algorithm, we will have different models usually. And to evaluate these different models, we do the k-fold cross-validation, and for each model we get a performance estimate. So here, for example, we will have 3 different models and 3 different performance estimates. And based on these, for example, using the one standard error method, we select the best performing model. And then in the next step, we take all our data, training data, choose the best hyperparameters and fit a new model using a learning algorithm. And the reason why we don't pick the model that was produced here is this is a model that was fit then on more data. So here, like we said before, like on the learning, as we've seen in the learning curve, more data usually doesn't hurt. So why shouldn't we use more data now that we have evaluated or selected our model? So we choose the best hyperparameters, run our algorithm again using the whole training set, produce a new model, and then we can use the test data to evaluate our model. It should give us a good estimate of our performance, and this is maybe what we report to our collaborators or publish in a paper or something like that. So this is a test set that the algorithm hasn't seen before, so it's an independent test set. And finally, once we have our performance estimate, I mean, again, there is no reason why we shouldn't use all the data. Maybe our model will become even a little bit better, maybe not, but why not using all the data? So typically, we can also then fit our model on the whole data set because the model evaluation stage is past us. We don't need to withhold this test data anymore. Just let's merge training and test set and train our model on the whole data set. So this is for model selection. And yeah, I mean, this is a very short talk. Usually, I think it's a very big topic, and I went over it very briefly. But just to have one more slide on algorithm selection, because typically in machine learning projects, we also don't know which algorithm performs best on our data set, so we want to also choose between different algorithms. And yeah, I think there are different approaches. So what some people do is they do k-fold cross-validation like before. They get different results. They use like hypothesis testing, maybe a paired t-test or McNemar's test and things like that. But there are also like 20 papers that they say that these are having an increased type 1 error, like false positive rate. Some people say it's a good metric. But usually in practice, what most machine learning practitioners prefer is a so-called nested cross-validation. And here, I mean, it's a very similar idea to k-fold cross-validation, but now we have 2 nested loops. So here, there would be one example. Just because I don't have so much space, I only have 5 outer folds and 2 inner folds. And how this works is basically in the outer fold, we have again a training fold and a test fold, and we take then the training fold for each algorithm, take the training fold, have an inner loop where we split the training fold again into 2 subparts, and then we optimize hyperparameters. So we do a model selection here, and for each algorithm, so for example, we get a best model on one particular training fold, and then we repeat this 5 times for this algorithm, and then we can. So what can happen is we can have for each algorithm 5 different models that have best hyperparameters that are different for each other, and this may be annoying, but I think this is a very important piece of information, because if the hyperparameters are largely different between these folds, it tells us our model is unstable. Somehow, depending on how we split our data, it learns different hyperparameters that are optimal. And if we do this for different algorithms, we can look at the performance of the different algorithms on average on this outer fold, but we can also see which algorithm is the most stable one, which is more robust to the kind of how we split the data. And then, similar to the one standard error method, we can come up with a way that we also look at algorithms that are stable based on how we split our data set. Yeah, so this is more like the way I think that is better for algorithm selection. It's less biased than running, for example, cross-validation on a training set and then selecting different algorithms on top of that. So you can think of it maybe model selection is one layer of selection, so we need a certain split procedure. And if we add another layer, like algorithm selection, we have to even add one more layer, like a nested layer. And yeah, there also, I think in scikit-learn, it was usually a little bit complicated to do nested cross-validation, but since the latest version kind of factored out the outer fold method, not method, but the outer, what is it, cross-validation function. And now there's also an easier example to do this in like 2 lines of code. I think if you Google for it, like scikit-learn nested cross-validation, you find something how to do this in practice. And so I was talking about model evaluation a lot, about accuracy of classifiers or regression models. And also I gave a little talk at Randy's workplace on Monday, and I thought this is also something that is maybe something worth considering. So beyond just mere accuracy of our classifier, also it's sometimes important to also check if our classifier really makes sense. So do our features make sense? So good features are usually features that discriminate classes from each other or are good for linear fit or things like that. But also good features, they should be salient, they should make sense, they should tell you something, and they shouldn't pick up something that maybe works well on our data set, but is somehow not, doesn't make sense in the real world. And for example, there was a paper on, the method is called LIME, locally interpretable model agnostic explanations. But they had a nice figure. So what they did is they trained 2 SVM classifiers. The one SVM classifier had a 94% performance, and the other one had a 89% performance. And they trained these classifiers on the 20 newsgroup dataset. So the 20 newsgroup dataset is a dataset of like an email list of people who are discussing different topics, and they trained the classifier to predict whether the article or email is about Christianity or atheism, and they trained these 2 different models. And the left model was the one with 89% accuracy, and the right model was the one with 94% accuracy. And they had all the right procedure, training set, independent test set, and so forth. But when they looked at what feature the model used, they found, for example, that the DataPhilly model picked up some weird features, like it didn't really look for anything useful in the model, like they picked up things that were unique to some subject header in the email by a certain person who was usually posting in the atheism group, for example. And the model kind of learned this because the test set and the training set both had an overrepresentation of this one person posting this topic. And of course, if you do a model evaluation, 94% accuracy sounds really cool. It sounds like it's really useful in the real world, but if you look a little bit deeper, you can think of that this classifier would be really useless in the real world, where you don't have a person called Paul D posting something. Anyway, so I would also say maybe the left features are also not that convincing when I look at them, but certainly more convincing than something like NTP posting host and something like that. And anyway, so I think, yeah, I'm right here at 30 minutes or so. So I should maybe stop now, and I have to say thank you for the invitation here. And yeah, if you have any questions, I will be around for an hour or so. I'm not sure how long we stay here. But I also have my email address or Twitter account here. If you want to ask me questions, I'm always happy to discuss topics, because I realized, I mean, that was a big topic and only 30 minutes was a little bit challenging. I hope I could maybe get you interested in looking into model evaluation in more detail, because I think it's a very important topic. I mean, for developing evaluating algorithms, and everywhere actually. If you don't do the model evaluation correctly, it can be very misleading, and maybe you are dissatisfied with your results. And I think it's a very important topic to pay more attention to, also in literature. And yeah, I thank you again for the invitation, and maybe we have a few more minutes for questions. I'm not sure how tight the schedule is here. Ah, okay. Yeah, thank you.
Can you go a bit further into the nested cross-validation? Back to it, and even a little bit further, because I'm completely with you on the K-fold the shift to the nested cross-validation, it will get it.
So maybe you can think of it, let's maybe blend the left part out, the alternate, and say you have only one training set. And then you can think of it as a regular cross-validation. In this case, it would be a two-fold cross-validation. So what you do is you have an algorithm, and on the training set you do a regular k-fold cross-validation. And here you have also different hyperparameters. You repeat this basically. It's you can think of it of this one, similar to the one that I showed before here, just with 2 splits instead of 5.
And you do this for each of them before you choose like you first for each of them do the bottom part of the k-fold inner for each of them, and then you do the outer comparison, or you first choose your algorithm and then you do the. I guess that you would do first the inner loop for each of them.
So maybe to step through it with an example, let's say we have a nearest neighbor classifier. We have only, as hyperparameter, we only have the number of neighbors. So we take our 3 nearest neighbor or nearest neighbor algorithm, and we start at the very top in our loop here, and take the training fold and the nearest neighbor algorithm, and then we do the k-fold cross-validation here, and find that 3 nearest neighbors works best. We get a performance here, and the performance helps us for model selection, like 3 nearest neighbor works best. Then we go to the second row, again a nearest neighbor algorithm, a different data set now, a different training data set, and we again do a model selection here. And maybe now we find that 4 nearest neighbors works better. And then we do the third row, again a nearest neighbor algorithm, and model selection, we find again 3 nearest neighbors performs best. So we get then, if we repeat this 2 more times, 5 different performance estimates for 5 different nearest neighbor algorithms. And then we compute the average performance. And then it should be actually also here this should be a 5 and not a 10. 1 over 10, over 5. And then we have 5 performance estimates in the average for nearest neighbor algorithms. So a nearest neighbor algorithm has then maybe 90% performance. But it can be that, for example, in the first row we have 3 nearest neighbors, and in the second one we have 4 nearest neighbors, and then 3, 3, maybe 4 again. That tells us also a little bit how stable the model is, depending on the training test split. But on average, for example, we can say maybe the nearest neighbor algorithm is expected to perform somewhere around 90%. And then we can maybe do the same with a random forest or with an SVM. And based on this average performance, we can get an idea roughly how well an optimized algorithm could perform. And then once we are finished with this, we can again use the regular k-fold cross-validation to do this on the whole training set instead of subsets. So you can think of it, the algorithm selection, as inserting it just before this step here, the second step. But before we do this, we do an algorithm selection. And then if we selected our algorithm, we do again the model optimization on a slightly larger training set. Yeah, another question?
Yeah, I have a question about the outer inner loops as well. Is that, can you make that kind of like a Bayesian process where you're taking information from prior loops and then incorporate information from those prior loops into your successive validating subsets?
I'm not sure if people have done this, and thinking about this, I'm not sure if it could introduce an additional bias, but it could certainly maybe be useful to narrow down for the second search, the hyperparameter space to search. It could improve it, but yeah, could be done. I haven't seen it done yet, but yeah, it could be done, I think, yeah. Another question? Yeah, sorry.
Sorry to keep going with this, but so just to clarify with that inner loop, so with your example of the 3 nearest neighbors, so would we be doing cross-validation where we do like, where each of those rows is a different number of neighbors, or you do?
Could be. Mm-hmm. So we could end up with the best model that has a different number of neighbors. But ideally, they would all have the same nearest neighbors as best hyperparameter. So here, for example, in the inner loop, we would say try the inner cross-validation with 1 nearest neighbor, 2 nearest neighbors, 3, 4, 5, 6, 7, 8, 9, 10, and what is ever best, what works best, gets passed back and evaluated on the test one. And it can be, depending how sensitive our algorithm is to different splits, that it is a different hyperparameter that is better than in a certain iteration. But ideally it shouldn't be different, because that would tell us our algorithm or our training set is really representative and our algorithm doesn't pick up any noise in the training test set or something like that. Yeah?
Yeah, two-part question. The first one, I was curious as to your opinion of using bootstrapping versus cross-validation for algorithm for training. And the second part of that question is do you know if there's like a bootstrapping equivalent to nested cross-validation for algorithm selection?
So the question was my opinion on bootstrapping. So I think bootstrapping is a very useful procedure. I just skipped over it because it's an alternative procedure. It's not so often used in practice because it requires way more effort. So you can do so bootstrapping is basically, you can think of it as maybe repeated train test faults, but how it works is you have your training data set and you draw a new sample of this training data set with replacement. So your new sample has the same size as a training set, but some records can be duplicated. And then the ones that are duplicated kind of take space in this n-size training set. So you have some samples that don't appear in the training set, and you use them as out-of-back estimates as a test set then. So the problem is there are different corrections for this method because they observed also bias of this method, and there's a follow-up. It's called 0.631 bootstrap, 0.631, because asymptotically you can show that 63.2% of the samples in training set due to this random sampling are only unique. And there's some correction term, 0.632 correction term. And then there's also a method to correct against another bias into the other direction. It's called 0.632 plus bootstrapping or something like that. And that is a equation where you also have to learn the weight of this coefficient that corrects for the bias term. So it's a pretty complicated procedure, and there's also a whole book on that by Tipshirani and Hasty, I think. And there was one paper, I mean it's a useful method still, but there's one paper by Ron Kohavi. He wrote this in 1995. I don't have the title now in mind, but he was comparing cross-validation, k-fold cross-validation versus bootstrap, and on different data sets and like diverse data sets, mostly small data sets. And what he found is basically that 10-fold cross-validation offers the best trade-off between variance and bias, like the sweet spot. And I would say it's more intuitive, easier to do, maybe more efficient. So in bootstrapping, you also have maybe more rounds than here. Here you have 5 rounds, and bootstrapping you have maybe 200 rounds. It makes it also more expensive. Bootstrapping is certainly useful, maybe useful to look into it, but I think for the normal person, like the accepted way is cross-validation. And I think the second part was if there's a nested cross-validation, like a bootstrap, like the nested cross-validation. I'm not sure about that, but I think you can do something similar also with bootstrapping, with an out-of-back sample that you have something set up. But I haven't seen this in practice yet. Yeah, last question. Well, I'm not sure how much time we have. We have like 1 more. Okay.
If you're doing feature selection, Hasty is a big proponent of doing it within your cross-validation.
Mm-hmm.
Do you have comments on that?
Yeah, so there was also, the question is whether or not we should do feature selection inside or outside the cross-validation. Usually, I would also agree with you or Hasty that it's better to do it inside. It's more unbiased. It's meaning that we are not peeking at any, we don't have any prior information. So each time we do cross-validation, we pretend that we don't know anything but what's in our training set here. And if we would include the feature selection on the whole data set or do it, then it's kind of cheating, it's looking ahead. But sometimes, I mean, there was one person, the name starts with R-H-A something. I can look it up maybe. He did a comparison and he also found that sometimes one is more biased than the other. There's no really, so the thing is, the problem is that there's no real consensus, so there's no real mathematical justification for anything. It's mostly observed empirically what does based on simulated studies or empirical real-world data sets. And also there's a paper by Joshua Benju, there's no unbiased estimate, cross-validation estimate, so there's no way to do it really unbiasedly, so the goal is to minimize the bias of basically finding the sweet spot between variance and bias. Yeah, okay, I think I should